Hello everyone, I'm starting the session. My name is Satyakam Pratap Singh and I'm your TA for this session. And the topic of this course is that is Smart Grid Basic to Advanced Technology. Whose instructors are Professor N.P. Padisar and Professor Premlata Janama. And this is a 12th tutorial session and I'm a PMRF PhD research scholar at Grid Integration Laboratory IIT Bombay. So before starting the sessions, for the today's topics will be certain like DC microgrid and some of the demonstration I will take from these sessions itself that and other some of the questions based upon that. So starting the first session of this first topic, that is a typical architecture of the DC microgrid. If you see that there are some in the image itself, you have a this DC voltage is there and some PV panels it being connected through the DC to DC converter through this DC bus bar, and some DC storage system is also connected. Some of the suppose the battery is there which is connected directly to this DC bus bar through DC converter. And for the AC bus bar, if you see that this is the AC bus bar, and from the DC bus bar to AC bus bar, it is actually used for the conversion of the DC to AC system, that is the inverter itself. And in between you have a L filter. This filter can be of different type, that a L filter or LC filter or LCL filter, and different kinds of filter you can use. But after the conversion of this DC to AC system, Chandrasekhar, can you please switch off your mic? Thank you. Uh, for the conversion of DC to AC system, you have a this DC to AC converter in between, and in between you have a multiple filters for the reduction of the harmonics from the grid side itself. And this is the, if you see that this LC filter is there which is connected in between, and after that this is the LF, and after that this is a point of common coupling at which the loads can also be connected and all. And this is a switch SW1 which is connected here, and this is the PCC. And this is the typical DC microgrid which you can encounter in a real life scenario, and it is through this PCC. If you see that this PCC is there and this is the grid. So from converting from the DC, then DC to AC bus bar after connection, then it is connected to the PCC, then to the grid. Okay, and it have a multiple section interface in DC devices such as PV, BSS, and ultra capacitors and all, and the DC loads. And if you see that there are control layers are there are four types of control layer. First control layer is the zero level control. It is for the control of the grid tied inverter variables, and and above that you have a primary control for the automatic load sharing and the grid support. And the secondary layer is the microgrid synchronization, the V by F control. And tertiary control, if you see that this is a for the optimization, the power flow control. So this is the first layer, that is a tertiary layer is a slow response. It is a time frame, if you see that greater than 10 seconds is there. And in this and the secondary and the primary, it is a dynamic means that it is real time which is happening into the system. And the zero level control is of a less than 0.1 second. So this is the four type of control layers are there in this DC microgrid situation. And there are two things are there. One is the islanded situation and the second is the grid connector system. By operating this switch SW1 and SW2, you can connect or disconnect this microgrid and operate in the islander situation or the grid connector system. Or you can operate in the autonomous system also by switching off this switch 1 and switch 2 at a particular time frame. So switch 1, if we close this switch 1, this is connected to here SW1, and this SW2 is closed. Okay, SW1 is open, and this SW1 and SW2 both are closed. So the DC microgrid is under grid connected mode of operation because both our system are being closed and this grid is connected directly to this PCC. Okay, and PCC is connected to the AC bus bar. And if switch 1 is closed, suppose this switch is closed but the switch 2 is open, so it represents that it is in an islanded situation because there is no connection with of grid with this microgrid setup. So suppose if the both this switch 1 is open and switch 2 is open or closed. In this situation, the DC microgrid is under autonomous mode of operation. It serves the DC and the AC loads only, because if you see this is the generating units and it is connected to DC bus bar. After that, it is connected to AC bus bar by DC to AC converter, and switch 1 is open. So it can supply the AC loads and it can supply the DC loads at their bus bar placement, but it is not connected to grid, so extra power it will not generate at that moment, so surplus energy should not be extracted in this situation itself. So coming to this question, that is the which I have told you, that different types of control mechanisms are there. This primary and secondary are for dynamic, and tertiary is a very slow response greater than 10 second, and the zero level response is really zero point 0.1 second, it is less than. So these are the different types of control dynamics inside of this DC microgrid. So this is a matching kind of question, but only you have to tell me that which type of control is used for the for which type of features. Suppose this is zero level, so zero level control is used for which situation, that is automatic load sharing, grid support, or anything. I'm giving you few minutes to solve this question. You can use also this theoretical knowledge to check that which system should operate fast and which should operate in the slow manner. Suppose the synchronization is there, if whether it is a dynamic or something. So the time taken to synchronize will be less or more based upon that which controls will be used, primary, secondary, or tertiary. So by that you can also guess the answer. Any answer from anybody? Uh, uh, you can give the answer. If it is a wrong, there is no issue in that. We will re-verify the answers and all. Okay. Chandrasekhar Reddy is asking some question. Yeah, Chandrasekhar, you can open your mic and ask me.
Hello, sir. Sir, I can
Yeah,
understand this problem, sir.
yeah, Chandrasekhar. Okay, let me explain you. So
Okay.
please close your mic. Okay. So question is like that. Suppose this DC microgrid setup which I have told. Let me erase few of the things here. Okay. So here what I have told you that this is the DC bus bar is there. This DC bus is there, and second is this AC bus bar is there. So what I have told you that this DC bus bar should be connected to the DC generating sources or the DC loads, and this AC bus bar should be connected to the AC loads or AC generating systems. So for connecting this DC to AC, you need a one inverter and the one filter. And if you see for connection with the grid, this is the grid, and this grid is connected to the PCC, that is a point of common coupling, through this AC microgrid. Okay, so through switch SW1. So when you are connecting this grid with this microgrid setup, so there should be a control algorithms or control features should be involved in that. Because why? Because if you are connecting this grid, okay, so this AC system, this which is generating by this inverter, the possibility that it have a harmonics, suppose in the grid you don't need the third harmonic, but your system is generating third harmonic at a lot. Okay, so it can be due to the load which is connected to the system, or due to the generating source, which when the generation is very low. So this two kind of system can happen. So this control feature is such that it should reduce the harmonic which is injected inside of the grid through this microgrid setup. So for that you need the proper tuning of the variables. Suppose you are using this PI controller by sensing this VG, that is a grid side voltage, and this IL is the inverter side voltage. So by offering this, you are connecting the systems and you are using some inner control loop for this harmonic injection and reduction. So for that features you need the tuning of this PI controllers. For that you need the control features inside of this. That is a you should tune that based upon that the harmonic reduction and all. Second is that if the load sharing got increased or decreased, based upon that your system should adopt in that situation that load is got reduced. In this situation, if the system is operating in the autonomous mode, so the generation should be reduced in such a manner so that it should generate only that portion which is necessary for the load. So this is the automatic load sharing. So this is a one kind of control feature. Third is the grid support. Grid support is such that if you are generating the extra power beyond your limit of the loads, so this extra power should be fed to the grid, but you cannot feed directly to the grid. You must have a certain control features in between, so that you are sending the power based upon the power quality and all. You must have the control feature that comes into this primary control features. In the secondary control feature such that this is the microgrid synchronization, because if you have a voltage generated from this inverter, that is the AC voltage, that is three phase AC, and your grid is also a three phase AC system. Okay, so your voltage of the A phase should synchronize with the voltage of the A phase here, because if it is not in the synchronism, so there is a means mismatch between the magnitude and mismatch between the phase. So you cannot actually utilize the system, and it causes the distortion in the power quality itself. So you need to synchronize the voltage which is generated from the inverter and the grid voltage. For that you need this voltage magnitude and the starting point of this your phasor. So that is the secondary control. And thus in that also you have a V and F control. V and F control means same as that. Voltage means voltage magnitude and the voltage same waveform, and there's and F is the same time frame, because your grid is of 50 hertz. Your inverter should also generate the 50 hertz supply. After that only the synchronization can be happen. In the tertiary, if you see, this is the last stage. In that feature you need the optimization. Optimization means you should take care of the extra power which is generated, which is sent to the grid in a high quality manner. And in that also you should utilize this AC load. And suppose there are two features. Suppose you are in a on peak time. Suppose you in the morning peak or the evening peak. In that situation, what you do that if you are generating a more, you should provide a grid support. For that you need the optimization of the power flow control. So these are the various features of the control mechanism when you are connecting a DC microgrid, or you can also say that the AC microgrid if you are connecting with the main grid. So you need a control features in between. You cannot directly connect this DC microgrid with the main grid. You need synchronism, you need optimization, you need the power flow control, you need harmonic optimization, and these are the multiple types of control features. So in this question, if you see that what I have told that this zero level is the control. Are you comfortable, Chandrasekhar?
Yes, sir. I
I think
told
I
you.
have answered your question. Okay, okay, thank you.
Yes, sir.
Shouldn't
Yes.
I given the answer as A? That is correct. That if okay, okay, that's correct. Actually, this is the zero level response. When the tuning of these parameters happen, it is a very slow response, means fast response. This time taken is the less than 0.1 second, and the this primary and secondary when the synchronization happen and the voltage and frequency control happen, these are the dynamic. Dynamic means you don't know the system when it can happen in the can occur in the grid connected system, when it go into islanded situation, when it operate in the autonomous fashion. So you need a dynamic control in the primary and secondary control, but in the tertiary for the optimization, the power flow control, it's a very means a slow response. It takes the 10, greater than 10 second for the controlling. So zero level control is control of the grid tied inverters variables. Primary control is the automatic load sharing and the grid support. Secondary control is for the microgrid synchronization and the V and F control. And the tertiary is for the optimization of the power flow control. So option A is correct. So let's move to the other part. That is the this is related to the DC microgrid and the ESS system. So there are five statements are there, and you have to tell me that which statements are true and which are false related to DC microgrid architecture. Okay, I got one answer that all are correct. Okay, anybody else? I'm giving you some few more minutes to check whether all are correct or not. Just go through the statements, all the statements. Anybody else who want to give the answer? Uh, if you got the first two statements or the three statements, you can also write in the this that first is true or the first is false. Kind of thing. Okay, he's having doubt on three and fifth. In last 1 minute. Okay, let's read the statements first. Okay. Coming to the first statements of this question, it is saying that a typical architecture of the DC microgrid include multiple distributed energy resources, that is DERs, such as the solar panels and the wind turbine. That is true because it this DC microgrid have a multiple can be connected to the multiple distributed energy sources, because if you see that you have a DC bus bar, you can connect with this DC bus bar by using some DC to DC converter if you are generating AC, and if you are generating AC you can also connect with this AC to DC bus bar. So you can also connect the multiple distributed energy sources with that inside of this DC microgrid. That is true. In the second question, second statement is telling that in a typical DC microgrid architecture, energy storage system ESS like batteries are often integrated to store surplus energy for the later use. That is also true because in the DC microgrid structure, the energy is being generated from the PV mainly, and you have a battery as a backup. When the PV is not generating much, but your load requirement is high in this situation, your battery should discharge to meet that load. And this battery should be charged during this off-peak hours when the tariff is low. Okay, so these are integrated to store the surplus energy for the later use. Coming to this third statement, it is saying that the power converters are not necessary in the architecture of the DC microgrid as all components operate on the direct current. That is false. Why? All systems do not generate DC. So if it is generating AC, you need the converters in between for connecting with the DC microgrid. In this image also, if you see in the right side image, you have a fuel cell, it can use the DC to DC interfacing, DC to DC converter in between while connecting to this DC bus bar. But if you have wind turbine, it generates AC, so you need the AC DC converter for the converting to DC, and DC DC converter for boosting up to the level of DC bus bar. And in case of the PV array, you need this DC to DC boost converter using MPPT control. And in the energy storage, you need directly the DC to DC converter, buck boost converter. Okay, so this kind of various converter is being utilized into this DC microgrid. So this third statement is false. Coming to this fourth statement, it is saying that DC microgrids commonly incorporate a central controller to manage power flow, voltage regulation, and the fault detection. That is true. Why? Because you need a controller. Controller means which is means controlling this power. If you see that this is the line which is being connected. If you see this is the double arrow, it means the bidirectional power flow. This is a unidirectional arrow, it means the unidirectional power flow. So this all features, it is being taken care by this controller. If you see that this is a controller, this is the upper control level, secondary control level, and the tertiary control level. So all control have to be inside of the system, and this central controller will decide when to operate. Suppose it is in isolated mode, means islanded situation. So this whole power should be absorbed somewhere. If you don't have any load inside of this controller, so there is no meaning of these generations. So in this situation, the control's logic should be such that it should not generate the power in that moment. So the central controller is must for the power flow control, a voltage regulation, and the fault detection. Coming to this fifth statement, it is saying that in a typical DC microgrid setup, loads are directly connected to the DC bus bar, minimizing the need of complex AC DC converter equipment. That is true. Fifth is true because if you have a DC means load, you can directly connect with this DC bus bar. There is no need to this convert to the AC, then AC to DC, then you can use. You can directly use the DC bus bar and connect this load. And suppose that your voltage level is not that much, you can use the DC converter for reducing the voltage or increasing the voltage based upon your load required. So fifth statement is actually true. So you can connect. Okay. So coming to this flexibility part, that is the features. Features of the DC microgrid are as such as it can provide the grid support when the generation is more. And in the last tutorial session, I have explained that various concepts such as the peak saving, uh, load reduction, load reduction, leveling, power leveling of the load curve, and the shifting of the load curve. So the various terminology I have explained in the last tutorial session. This DC microgrid can provide that support, that is the grid support, stability when the generation peak hour is there and you can generate and feed the power to the grid. Flexibility is there, you can generate that power and you can absorb the power in the battery itself. And the scalability, you can use this a microgrid setup which is a small level, you can use the anywhere. Suppose in the model concept is such that you should utilize the every place which is there for the green energy aspect. There is a concept of floating solar panel, so they are utilizing this solar panels on the lake, ponds and itself. So they are utilizing the places where they can use that and scale that. Okay. So major functionalities of the DC microgrid are the grid voltage and the frequency support, which I have told you. Coordinated voltage forming and the voltage sharing, harmonic attenuation, which I have told in the using these control features, energy management between the grid and the microgrid, and serving the critical load during the grid outage. Suppose there is a no grid is connected, so this DC microgrid can operate in the islanded situation and fulfill the load requirement. And this DC microgrid can able to work in the both this normal and the abnormal condition, which I have told you, that is a grid connected in the islanded situation. And it can also operate in the autonomous mode when it is not connected to AC loads as well into this inside system, and also it is not connected to the grid. Okay, so in the right side image there is a multiple control features that has been given, and the various power quality issues are also given and how it is being mitigated. This slide I will share, you can read that. And the major focus areas of this DC microgrid, that is the grid connected in the islanded situation, and this is the actually typical setup if you see in the slides. This is a typical DC microgrid setup which is utilized in the present scenarios. Suppose you have a DC microgrid that is generating sources, you should connect into this DC bus bar, that is a capacitor if you could see. This is for the ripple reduction, and you can also use the DC loads inside of this directly connecting to this DC bus bar. And this setup for the laboratory experimentation, this setup, whole DC setup will be there in the OpenRT. For the this I have told you in the previous lecture that this is the RTDS, real-time digital simulator, which synchronizes with the real-time clock generating system. So this DC bus bar, after that you need the DC to AC converter. After that you need the L filter for reducing the harmonics and for getting this smooth AC system, sinusoidal smooth signals. And you can connect after that with the PCC at AC loads also and with the grid also. And this PWM control of this inverter is being generated by sensing the voltage at the point of common coupling and the current which is fed by the inverter, that is the UAVC and IAVC. It is being sensed using some Hall sensors. It can be used for the current, and this UABC for the voltage sensor it can be used. And after that it is feeded, it is converted to the digital domain, because your pulses is being generated in the 0 and 1 logic. So these analogs have to be converted into DC, and this digital domain. After that, UABC, IABC have a digital component. It is converted into alpha beta frame for the controlling features. This is easy in conversion with respect to this ABC. The DQ frame and the alpha beta frame is very easy for controlling. And inside of this control logic, if you see that DC bus bar control and the inner control, okay. After that, this whatever the PWM is being generated, it is fed to this AC DC to AC converter. So this is the basic typical control algorithm, not control algorithm, but a basic setup for the grid connector system. So I have one question related to this DQ frame and the alpha beta frame, how it is being converted. So this is there are the five statements are there, and you have to tell me that which statements are true and which are false. Because in the 11th tutorial session and the 10th also, I have explained this in the thorough. I will explain today also, but I hope you can solve this question. Okay, Yadama is asking that, sir, but loads may be AC like motor. Yes, it can. It is actually AC. Majority of the loads are AC, but there are some DC loads are also there, which utilizes DC power directly. So in the laboratory, we use this rheostats for means utilizing the DC load. Behavior of this DC loads is being mimicked using rheostat. For the AC load, we use the generally bulbs. So there are multiple type variety of loads are there. Okay, he is asking that how the fifth statement is true in the previous question. Okay. Uh, if loads are AC like motors. Okay, actually, Yadava Gukara, please solve this question. After that, I will come to your this doubt. Okay, I will clear this doubt after this question, because the everyone is solving this question. There will be some interruption in between, so I will take it after this solution of this question. If you are having any doubt, just let me know. You can write in the chat box or you can open your mic and ask me. If you are facing any difficulty that you are not understanding this question, let me know. I will make you understand. Okay, Chandrasekhar, you can ask. Chandrasekhar, you can open your. Okay, you are not able to. Your voice is not clear. Chandrasekhar, your voice is not clear. Uh, you can write in the chat box. Okay. Again, explain this topic, this DQ frame, or last topic that energy storage systems or this control algorithms, that whole setup. Okay, this topic. Okay, sure. I will explain this question. Uh, Let me take you to this topic, that is the alpha, beta, and DQ frame. After that, I will directly come to this solution part of this. Let me take you to this class and the path transformation. Okay, so let me make you understand this actually class and the path transformation. Actually, the performance, suppose you have a AC machines are there. So it's a rotating machines, no? And if you take the synchronous machine, you have a two things, that is the rotor and the stator. And on rotor you have a field winding, and on the stator you have armature winding. And this whole system is in rotating frame. Okay. So this whole system, if it is rotating, so it's become very difficult for any control system or control algorithm to implement in this rotating frame. What will happen that is a some machines, that is the inductance. Suppose you have this stator is there and the rotor is there, and this not cylindrical level. Suppose there was this is silent flow rotor. So this is the reluctance are variable. And if you see that this reluctance in the this D axis, if you see, it's a high. This reluctance is more. So in that, if you see that the MMF is low. So MMF is low, it means that the storing capacity is low. That is a flux storing. So it means that the inductance is also low in that system. But if you see that Q frame, if you see the gap is very low, so the flux can directly transfer to that, and the reluctance is very very low, and the MMF is very very high. So actually the main crux is that the L is variable. Means why variable? Because the reluctance is variable. In this situation, you have to write the multiple equations when it is rotating. Suppose your rotor comes to this position. So then you have to write a different equation. Then suppose it comes directly to the d axis. Then you have to write a different equation. So the coefficient of the differential equation which describe this whole situation, this behavior of the electrical machine have the time varying aspect where the rotator is stalled. Okay. So change of variable is often used to reduce the complexity of this differential equation. So there are several methods to transform this ABC frame, rotating frame, to the DQ or the alpha beta frame. Okay. So this class in the past transformation mainly property utilizes this electrical machines, which reduces the complexity in the voltage equations, because in the EMF you have all the component, the mutual component, the self component, and these all are the time varying components. So this alpha beta and the DQ frame are very easy to utilize and design any control system. Okay. So coming to this class transformation, if you see that this is the alpha axis and this is the beta axis, and it is a three-phase system. Three-phase system is this is A, this is B, and this is C. So if you see that this is the means A axis, which is a angle 0 degree, and this B is angle 120 degree, C is angle minus 120 degree. In this frame, this is actually a time varying situation is there, because if you write the V is the Vm sine omega t, Vb is Vm sine omega t minus 120 degree plus or minus 120 degree, or Vc is the Vm sine omega t minus 120 means minus 240 degree. In this situation, if you see that this is a time varying components. So time varying components means if the time is at 0, then the value will be different. At time is equal to 1 second, this value will be different. Time is equal to 2 seconds, all values will be variable. So what we do, we take this Vm, suppose this is Vm, then take the transformation in the two domains, that is take a x-axis component and the y-axis component. So this Vb is transformed into two components, that Vb beta and the Vb alpha. And same happens with this Vc. Vc have the two components, that Vc beta and the Vc alpha. So if you sum up all the alpha component and sum up with the beta component, you get that only two frames, which is not a time varying. Why? Because the alpha beta frame is there. It is not a time varying. It's only a magnitude component. If you see, it's all lie on the alpha, either on the alpha or in the beta frame. So alpha plus j beta. If you control this alpha and beta frame, you can directly control these ABC equations. Okay. So these are the transformation equations. If you see in the below this image, that f alpha beta naught is equal to t alpha beta naught multiplied by f ABC. This t alpha beta naught is the transformation matrix, that is a 2 by 3 times of 1 minus half, 0 root 3 by 2 minus root 3 by 2, and the half. So these are the transformation matrix, and you can also convert in the reverse fashion also, that ABC is equal to T alpha beta naught inverse this alpha beta naught, because it's an invertible matrix. Okay. So, and the second transformation is the Parkes transformation. Parkes transformation, what do they do? Because in the class transformation, this alpha beta frame is a fixed frame. In this situation, what they do, they take this component as also as a rotating frame. Suppose it is rotating at the theta value, so this alpha will come here and your beta will come here in this situation. So this situation is like that. This Clark's transformation is such that it is a stationary frame, and the Parkes transformation is a rotating frame with a theta degree. Okay. So this theta comes through this PLL. PLL is for the phase synchronization. So same way you have also the matrix here for the conversion of this ABC to DQ frame. This T QD naught, if you see, this is a theta component is there. This is a rotating angle, and this theta is equal to, because omega is equal to 3 theta by 2, and theta is equal to angle of omega dt plus theta naught, which is an initial sum angle is there. So this is the basic crux of the Parkes and the Clark's transformation for the control designing. So coming to this question, your question, always remember that Clark's transformation is for alpha beta, and the Parkes transformation for PQ frame, DQ frame. Okay. So P is for Q. If you say like that, you can remember. So coming to the question part. If you see that what is saying that this I have explained that the Clark's is for and the Parkes is there. Parkes is for DQ frame and Clark's is for alpha beta frame. Okay. So coming to this first question, statement, it is saying that Clark's transformation is primarily used for converting three-phase continuity from the time domain to the alpha beta reference frame. That is true, because I have explained that Clark's transformation is for ABC to alpha beta frame conversion, and ABC to DQ frame is for Parkes transformation. Coming to the second statement, what is saying that Parkes transformation, also known as the DQ naught transformation, that is true. It utilizes to transform three-phase quantities from the alpha beta frame to the time domain. Actually, this is for why? because it don't convert then alpha beta then convert to DQ. It directly convert from ABC to DQ frame. So second statement is false. Coming to this third statement, it is saying that past transformation is particularly useful in analyzing the behavior of the synchronous machines in the stationary reference frame. That is true, because I have told you that this rotating frame, that is a L, is variable, so we take it on the particular stationary frame. After that we utilizes that for the controller design. And in the fourth statement it is saying that both clocks and the past transformation are essential component in the field oriented control of the electrical machines such as the permanent magnet synchronous motor. That is true. Fifth statement is saying that clock transformation is also referred to the DQ naught. DQ naught transformation, it is commonly used in field oriented control strategy for the control of AC machines. That is false, because the class transformation is for alpha beta. So first 3-4 statements are true and the other is false. So if you have any doubt, just let me know in this topic related to class and the past transformation. After that I will jump to that doubt of one of the question of the student. Is there any doubt related to that? You can also read this from the multiple sources. This is the basic introduction of this sparks and the class transformation. Okay, let's jump to this doubt of one of the question. If you see here. Here in the fifth problem, one student having doubt that how you connect these DC loads directly here. So let me remove this. After that I will explain. Your fifth statement is saying that in a typical DC microgrid setup, loads are directly connected to the DC busbar, minimizing the need for the complex AC-DC converter equipment. Let me take one slide for explaining this. Suppose I am taking a very basic setup. Suppose I am taking a one PV module and of a certain voltage level, and the current is specified based upon the irradiance level. And the second, I am considering a battery for the storage and for maintaining the DC busbar link voltage. This PV should be connected to a DC to DC boost converter, but this is DC boost converter, and this PWM comes from MPPT control. And after that it is connected to a DC busbar, and same DC busbar is connected to the battery also. Okay, this is connected like this. After that you have DC to AC converter, that is the inverter. After that you have some filters. Suppose you have a LC filters. Suppose I have connected like this L. Then after that you have LC filters. Suppose like this you have a C component, and here also you have a one C component, and here also you have a C component. Okay, these all are connected like this. After that you have a PCC is there. PCC is such that this is suppose this is a point of common coupling. After that it will be connected to the grid. Okay, this all three phases. And in this situation you can also connect this AC loads here, because this is for AC voltage you get here, the AC voltage and the current. And the question is saying that you can utilize the DC busbar for connecting the DC loads. Okay, so if you see here in the question in this diagram, here is the DC voltage is coming, and this battery is connected through buck boost converter, DC to DC buck boost converter. So for generating a 230 volt RMS and a 50 Hz supply, you need a 600, suppose 600 to 750 voltage level at this DC busbar. Okay, so for maintaining that voltage, suppose the PV generation is not that much, so battery give the power to maintain this voltage of the DC busbar. Okay, so this act as a DC voltage source. If you see that this voltage source, you can directly connect a load across it. Suppose you are connecting a resistor, a rheostat. In this situation you can directly take the power from the grid, because this voltage is being maintained using, suppose it is maintaining at a 600 volt level. So this voltage is fixed. So I will be like that, 600 divided by RSH what you are giving. Okay, directly connecting to this DC bus bar. There is a no meaning of connecting to this DC load across this AC terminal by utilizing again this AC to DC converter. So the main crux is that you can use this DC load directly at this DC bus bar, and you can utilize this AC load at a AC bus bar. Okay, so this is the main crux of this question. Okay, I hope I have cleared your doubt. uh, Gokaram, I think I have cleared your doubt, and also Chandrasekhar. uh, okay, thank you. So let me go to these other topics of this session, and this is related to the control technique. That is the I've told you that various filters are there after AC to DC to AC converter. That is the L filter, LC filter, and LCL filter. And this is the basic diagram. If you see that, this is the AC connected system, and this is the LCL filter, and this is the three-phase inverter, and this is the DC bus bar, DC bus bar. And in the down image, if you see that, this is the single phase equivalent of this active rectifier with this LCL filter with the same features of this AC system. And this have a certain issues. Suppose you are using L filter, LCL filter, there are certain issues are there. Issues is such that you can, this L is there, you have a C. There is a possibility of resonance in between the L and C filters. If you see in the image, there is a notch at certain frequency, FC. This notch is related to this resonance frequency, that is equal to the 1 by 2 pi root LC. Okay, so this notch comes, that is magnitude got increased during the resonance features. So this is not actually important for this current scenario. So this is the only thing I have to tell you, that there is situation of the resonance, it comes into this LCL kind of filters. And the phase, if you see that this is minus 90, it is shifted by minus 180 degree. Okay, during the resonance features. So coming to this next topic is such that there is a one question in between, that is related to A ADC converter. So I think I request all of you to solve this question. Actually, it's a very easy question, but I request you to go through some ADC converter basic logics. I'm giving you few of the minutes to solve this question. Okay, I got one answer as maybe. Are you going to the logic or just guessing? It's okay. There is no issue in that. Last 1 minute to solve this question, because we have a more content to cover in the session. Okay, there is no issue in that. It's okay. Anybody else who is trying this question? Okay, let me explain this question. I will not go to the solution part, option A is correct, but I will explain the process. This is the 3-bit ADC converter whose reference V reference is given as 5 volt and the V input is given as 2.8 volt. So the resolution of this ADC, this first thing you need to know that ADC resolution. After how you can think of that. V resolution is V. Okay. Okay. Now you can hear me.
Yes, sir.
I think. Okay. Thank you. So this resolution of this ADC is such that V reference divided by 2 to the power n. To n is 2 to the power n. N is the number of bits. Here the number of bits is 3. So V resolution is equal to 5 volt divided by 2 to the power 3, that is the 5 divided by 8, that will come out to be 0.6254. Okay, so there are multiple 3-bit situation, 3-bit ADC is there, no? So logic will be such that 000, 001, 010, 011 and 100, 101, 110 and 11. So each bit is specified to the certain voltage range. Okay, suppose this is resolution of the 0.625, so 0 to 0.625 have a 0 logic, and above that 0.625 to 0.625 multiplied by 2 will be the second logic. Then after that 0.625 multiplied by 2 or 0.625 multiplied by 3 will be another logic, and last if you see there is a 5 volt logic. Okay, so this 101 will logic will come with this 2.8 volt, that you can check by that multiplying this voltages. Okay, so basic thing is that you need to know the resolution of your ADC and the voltage which you desired and at what bit it will come. Okay, so this is important. Coming to this next topic is such that this is the control logic in the DSP, that is the digital signal processor, which we uses. In this situation, if you see this DSP based controller, this is the grid connected mode. This DC bus voltage, that is the PI controller. If you see that, this is DC voltage at a reference value and generate this AC power reference, and the AC power reference that is the active control current reference is generated as a inner control required for the current reference. Okay, see in the first image, this is the pink image. This VDC reference is that what I have told you in the DC bus bar lag, that you have to maintain a certain voltage for the DC bus bar. So DC reference, suppose I wanted to take the 600 volt, so DC volt reference I have set it to the 600 volt. So whatever the DC will come through the PI controller, it will generate a P reference. After that the current will be generated, which is being used to feed into the system, that whether this battery to discharge or battery to charge. Okay, and the IQ is 0 because you don't want any reactive power into the system. Okay, so the nominal current which flow into the system, it's actually a IP square plus IK square, and also this nominal current, it should be equal or it should be less than or equal to. And if you want the IQ component to 0, this means the reactive power component to be 0, so I nominal will be less than or equal to the IP. Okay, so IP whole power will be injected into the grid. There will be no reactive power being consumed inside of the system. So this PQ frame is converted to the alpha beta, then it is compared with this references, then it is proportional controller, then it is compared with the U alpha and U beta. U alpha and U beta is such that which is taken from the U ABC reference at a point of common coupling. And this I alpha and I beta is taken from the inverter side output, inverter out. Then it is generated some PWM signal which is being utilized for generating this, giving this signal to the this DC to AC converter, that is inverter. Okay, So this is the basic control logic in the DSP. DSP is this digital signal processor. So coming to this next topic, that is the based upon this PI controller, I have told you that by comparing this signal reference which is being taken and what is being actual is coming into the system, this both in being compared, then it is fitted to the PI controller. After that, this error signal is being minimized. Okay, so based upon that, this question is there. So I think you can solve this question by simply the logics. Use the logic that transfer function is kp plus ki by s. Okay, and the error is v reference minus v actual. Okay, I got one doubt that he is not she is not able to understand. Let me explain further. Let me explain further by taking some slides. Let me explain in this image itself. So I am explaining this actually whole system which I have explained in the currently again. So if you see that there are two systems are there. One is the DC system which is connected, suppose the PV and the battery which is connected to DC busbar, and after that you have AC DC to AC converter, then you have a filter, then you have a PCC, point of common coupling, which is connected to the grid. Okay, at the PCC this voltage UABC is taken, and the after DC to AC converter this current reference, that I reference is taken here from the IL. Okay, so major voltages are UABC and major current are ILABC, that is the inverter output and this point of common coupling voltage. So and this DC bus bar have to maintain certain voltage for generating 230 volt in the AC side. What voltage is 600 to 750 nearly. So this DC reference is 600 volt and VDC is actual VDC which is coming. Though this PI controller reference is being generated, PI controller, then reference is generated based upon this IP star is comes out. IP star is the power which is actually needed. So IP star and the IQ star. IQ star is the 0. Why? Because the reactive component you don't want, you know, only want the real power. So real power is the IP component. Then IP component is converted into alpha beta frame for conversion by taking this U alpha and the U beta as a reference. Because ABC will be converted to alpha beta, and also it is connected to PLL for generating theta value. Because in the DQ frame you need the theta also, because it's a rotating frame with respect to alpha, means a theta. So then it is compared with the alpha and beta, then it is footed to the proportional controller, then alpha, U alpha and U beta is being compared, then it is generating some PWM pulses. Let me explain you with the slide, taking a slide in the more detailed fashion. Let me take one slide. Okay, so suppose there is a PV is there and you have a battery. It is connected to a DC bus bar, and pardon this drawing. Okay, it is connected to some DC converter, and this is also connected to DC boost converter. After that it is being converted to this DC to AC converter, and after that you have a filters. After that you have a PCC, point of common coupling, for the three phases, and then it is connected to the grid. Okay, so here I am saying that this UABC is there. This firstly this voltage and this current of this output of this AC voltages, that IL is taken as a reference, ILABC. This UABC is then fed to the PLL. PLL generate the theta value, which is the synchronizing angle. synchronizing angle, because it should is its angle should be same as what is being connected with the grid. Suppose it is generating 50 hertz, grid is 50 hertz, so it should also generate the 50 hertz. So for that you need the certain reference frame. So this theta is taken. After that, this theta UABC is converted into UD and UQ frame using some, sorry, this is not correct. Let me remove this. Suppose UABC is taken, it is given to the PLL. PLL generate the theta. Then UABC is converted into using ABC to DQ frame into D component and the Q component, UQ and UD. And this theta is also needed into the DQ frame, because I have told you that it is a rotating frame with a theta degree. So and then DQ frame, how you get this UD and UQ frame? Then it is fed to some PI controller for generating a smooth sinusoidal signal. What about the current? Current is taken, then it is converted into DQ frame, ABC to DQ frame. It also takes this theta value which is generated from the UABC. Then it generates the ID and the IQ. So this battery will be charged or discharged based upon the PV irradiance. Suppose the PV irradiance is 1000 watt per meter square. In this situation, this battery is not needed because it is generating as much as which is desired to maintain a 600 volt here. So what will be done here, that 600 volt is the VDC reference, and what is the actual is being observed here is the VDC. So VDC reference is 600 volt. So VDC reference of 600 volt and the VDC actual is being compared, and then it is fed to the proportional controller for generating ID and the IQ. This ID and IQ will be compared with this ID and IQ. Okay, then this is connected to the PI controller. Then this IQ is generated actually. Then this IQ is here. This is fitted to the zero level. This ID actually is to be generated and IQ is fitted to the zero value. Then it is fed to this PWM, then converted to ABC, then DQ, then it is fed to this PWMC. So whole system is such that it is utilizing the PV generation itself. Battery also went to charge and went to discharge based upon the maintaining this DC link voltage. So this is the main crux of this actually whole diagram. Okay,
Yeah,
are you
yes,
getting my
sir.
point?
One small doubt in that IL current, how it is generated,
Okay,
it depends on the load current or else.
okay. No, no, no. Actually, IL is being generated based upon your generation. Suppose that you have a PV generation is there and it is at a 1000 irradiance level. So the current will be higher in that irradiance. Suppose the irradiance lower down to the 500 watt per meter square, then the current will reduce. So based upon the generation capacity of the DC
Okay.
sources, this IL
Okay,
should
sir,
will be
got
differ.
it.
Okay. Okay. So this generating sources voltages are actually fixed based upon this battery which is being utilized, and the current is variable based upon the PV generations. Okay, so this is the main crux. So I request you all to solve this question. This is also a very important question related to the KP and KI value. I am giving you few minutes, 3-4 minutes to solve this question, or if you after that I will explain this question. Last 1 minute. Okay, guys, let me explain this question. Let's first read the question. What is saying that? It is saying that in a power system, a proportional integral controller is implemented to regulate the voltage at a bus bar. Suppose there is a one bus bar is there, and this voltage magnitude that V reference is needed is, that is 1.05 per unit, but the V actual which is coming is 1.02 per unit. So based upon that, I have used a PI controller which have a KP value, that is a KP value of zero point 0.1, and KI value is equal to 0.01. You know the transfer function, that is a KP plus KI by S. KP is the proportional integral constant, and the KI is the integral constant, and the 1 by S is the actually integral controller. So if the system operates for the 5 minutes, so operating time is 5 minutes, and sampling time, T sampling is 1 minute. So what is saying that desired V reference is 1.05 and the voltage magnitude is 1.02, Kp is 0.1, Ki is 0.01, and sampling time is 1 minute, that is the, and the operating time is the 5 minutes. Okay. So error is such that what I have told you, that this is the error, this VDC reference plus and minus VDC, and one error is generated. Error is equal to VDC reference minus VDC actual, VDC actual. So error will be equal to 1.05 minus 1.02 is equal to 0.03. Okay. So this is actually the error. So after error which comes into for the comparison, then we use this PI controller for the error minimization. Okay. So integral, what integral controller actually do? This is the, if you see that Ki by S, actually this is the integral controller. Okay. So this is actually a term, that is the IT is equal to IT minus 1 is equal to Ki ET. That's very simple. That is actually coming from this sampling. When you convert this integral controller into this sampling domain, means a discrete domain, that will come out to be, because it's an integral controller. Okay. So this is actually a Ki, 1 by S is the dt. No? So that is the same as Ki multiplied by D, that is multiplied by error, because the error is coming here. So error multiplied by Ki multiplied by the time is equal to the difference of the this samples, that is the IT minus IT minus 1. So IT as a present time is equal to IT minus 1 plus Ki ET. So I1 is actually what is happening, that I previous what was there, that is a 0, The I1 is KIET. KI is 0.01, error is 0.03, and T is the sampling time, that is of a 1 minute. If you multiply, you will get 0.0003 per unit. So basically, whole of the crux is that this transfer function is KPE plus IT, because it's a error signal, no? Error multiplied by KP plus KI by S. No? So it is multiplied with the KP and multiplied with the integral. So if you put the values here, that is the KP is equal to 0.1 and the error is 0.03 and IT comes out to be 0.0003, that will U will come out to be 0.0033. So this is the whole crux that and you can go also with the reverse stage, that if you have the U value, you have the error value, you can find out the KP and the KI value. There are multiple algorithms are that, such as the PSO algorithm, genetic algorithm for optimizing and getting this KP and KI value. Mostly people do with the hit and trial for selecting this KP and KI value. Okay, so coming to this next topic. Next topic is the which being explained in this lectures itself, that prototype. Just let me close my windows.
Sir, what is the option? I think so. There is no option related to 0.0033.
So, error is the 0.0 yeah, say I think the options are wrong in this situation. So the correct answer is 0.0033. So these are options are wrong. So error is 0.0033.
Okay.
So coming to this next topic, that is the laboratory prototype, which I already been explained how to test into the laboratory. There are multiple components involved in that. So this whole system, that is the DC microgrid, if you see that the connecting to the DC bus bar, this system is actually implemented into OpenRT, that real-time digital simulator, and the voltage level which is generated by this digital simulator output is a 10 volt plus minus 10 volt, and the current is also very low. So for connecting to this actual system, actual real world systems, so you need a power amplifier in between. Power amplifier, why the power amplifier? Power amplifier is being used for voltage increment and the power increment. Suppose power is there, no? Power is the VDC IDC and you are generating a 10 volt. So power amplifier will do that. This will enhance the voltages and enhance the current also. Okay, so based upon that, you will take out the actual power which is being generated into the system from the 10 volt to the, suppose it is taking 600 volt. So 10 volt is actually 600 volt in the simulation environment, but it is not actually in the real world environment. So for this actual environment, generating this 600 volt, you need a power amplifier in between. This is a power amplifier which is taking analog input from the signal and the analog out it is giving. And then it is connected to the DC bus bar. Then you have this DC to AC converter stack is there. The Micron stack, Micron actually the company which make this stacks. And then you have this AC LC filters, L filters here. Then you connect it to the AC loads. Then you have a Synergia grid simulator. Grid simulator says that you cannot connect the system, whole system with it directly to the grid due to the disturbance and all. So you simulate the grid into this Synergia. And this Synergia is actually being used for this grid connected system testings on all. And if you see in the lower side, this is the DSP controller. This DSP controller take the reference of UABC and IABC. This is the inverter side current and this is the point of common coupling voltage. Is take the UABC, IABC and VDC. VDC from where? VDC from here. This from this DC voltage bus bar. Then the whole algorithm will be installed into this DSP controller that I have told you, that KP, KI and all. It is actually implemented in the digital domain inside of this DSP controller. Generally, we use this F2839 this D and this is a low cost DSP controller. Then it will gives the logic to the actual AC to DC to AC converter stack. So this is a whole are the laboratory setup for this prototype for the grid tied DC microgrid. So always remember that you need the power amplifier if you are using the Opel RT system beforehand, because the Opel RT will generate only 10 volt plus minus 10 volt reference, but you need the 600 volt level at a stack voltage. So power amplifier will convert 10 volt to the 600 volt, that is the actual voltage which is being there in the simulation environment. After that we use this DC to AC stack, then L filters, then home loads by using lamps, then synergy as a grid simulator, and the DSP using for the controllers for generating PWM pulses for this inverter. And if you see this as a hardware demonstration, that is the more closed view. If you see that a more open view, that is the grid simulator, and this is the stack, DC to AC converter stack. That is the actually this is the power amplifier, and this is DC microgrid which is there in the Opel RT. And you can connect the DC load also using some rheostats and all. So this is the basic hardware setup. Okay, so if you wanted to pursue the higher education and all, then you will get a chance to actually simulate this kind of structure. So if I'm using the islanded situation, so islanded situation you don't need to have this Energia grid simulator into the system, because there is no grid. So only you connect this AC loads and you take the UABC reference and IABC reference and put it into this DSP controller and generate this PWM signal based upon your logic. And DC microgrid that is the same inside of this Opel RT, and you can also use this power amplifier in between. So here is such that the system here you can use this Opel RT in between this power amplifier, and you can connect this DC load at a DC bus bar. So this is actually the islanded situation where you don't need synergy or grid simulator in between. Coming to this next topic, that is the control logic, which I have explained also in that system, but this is the islanded situation. So in the islanded situation you don't have any voltage reference, but you are taking the voltage reference of UABC because the load is connected. If you see that AC load is connected, which need the 230 volt supply and the 50 hertz supply, 230 volt 50 hertz supplies. For that feature we sense this PCC voltage, whether it is generating that same voltage or not. For that we use this delta W. This is a droop based control for generating this actually ID and IQ reference. This droop based control will be used for IP generation. The IQ is 0. This is delta VP at the point of common coupling. Then it is converted into the alpha beta frame, and then alpha and I beta reference will be taken into the system. So this is the main crux of generator of system. That is same. I have explained that I nominal is equal to IP square plus IQ square, and this I nominal should be less than this should be greater than or equal to, and if you are converting this IQ is equal to 0, it means that you don't want any reactive power into the system. So I nominal will be generally nearly equal to the IP. Okay, so this is a basic you want to explain that you only want to utilize this real power, not the reactive power. Coming to this next topic is this is the laboratory setup for this islanded situation that I have explained, that the whole of the system here in the Opel RT, and you have a power amplifier in between, and you have a directly AC load in between, and you can sense that UABC, IABC and VDC and directly feed to this in this AC to DC converter. So only you need to remember these components and how it is being used and what points at which the sensors is being placed. Sensor means voltage sensor and the current sensors. And this is the grid tied DC microgrids situations, and here if you see, this is the actually battery storage system is also there inside of that, and the whole model is same. So I have one question related to this energy storage system. There are 5 statements are there, and you have to tell me that which statements are true. this whole statement is related to the battery energy storage system. I got one answer that all are correct. Okay. Anybody else who want to try? These are the very easy statements. If you read that, if you are getting two as a correct answer, you can also write in the chat box that you are correct. You have 30 more seconds, 30, 40 minutes, more seconds. Okay, let me read these statements. Sorry. Uh, Coming to the first statement, what is saying that in an islanded system, the power generation and the consumption are self-contained within a local network. Whereas in a grid connected system, the network is connected to the large utility grid. That is true actually, because in the islanded situation, power generated and the consumption is there is a inside of the same self-contained local network, because it is not a grid connected system. But in the grid connected system, network is connected to the larger utility system, and the whole the generation, if it is an access, it is sent to the grid. In the second statement, what is saying that islanded system are more resilient to the grid failures and the blackout compared to the grid connected system, because they are continue to operate independently. That is true, because it is an advantage of the islanded situation that can come in the statement based question in the exam itself, that whether which system is more resilient to this grid failures and all. In the third statement, if you can see that islanded system typically require energy storage system to balance supply and the demand within the local network, while the grid connected system rely on the stability and balancing services provided by the utility grid. That is true, because the islanded situation, if the generation is low, then you need a certain backup because it is not connected to grid. So you need a certain backup to supply the extra demand. In the fourth statement, if you see that in a grid connected system, excess energy generated beyond local demand can be exported to the utility grid, whereas in the islanded system, surplus energy must be curtailed or stored locally. That is true. When it is a grid connected system, the excess energy will be sent to this grid. But if it is an islander situation, your PV have to make sure that your PV should not operate in the MPPT mode if your load is less. Or you can make sure that if the battery energy storage system is there, so you can operate the PV as in the MPPT and store the excess power into the BSS. Okay. Coming to the fifth statement, that control strategies and the operational requirement differ significantly between the islander and the grid connected system, with islander system needing more sophisticated control to ensure stability and reliability without the support of the larger grid. That is true. Why? Because if you have a grid connected system, the reference of the voltage, that UABC, this is taken from the directly from the grid itself. So from based upon that reference, you can generate this power, this voltage which is being needed. So if it is not connected, this grid connected, this is an island situation. So how you can make sure that it will be same voltage as that of the grid, because you have to feed the AC load also, which take the 230 volts sinusoidal voltage supply. So this is a complex actually control algorithms are there into the islander system. So coming to this laboratory prototype of the grid tied microgrid, they have taken the two test cases, test cases such that they have implemented this DC microgrid into this, and their power amplifier they have used, and the control system interfacing the DSP, which I have told that power amplifier is there. You have a Opel RT is there. You have a DSP controller is there. You have a grid emulator is there. So these are the main devices which is being used, and this whole DC system inside of this microgrid, and this grid emulator is forming as a grid, and DSP controller is for the controller design, and the power amplifier for boosting the voltages. Okay, so this is a big setup. So first test case is that if the sum of the power generated by the PV and the BSS is more than the DC bus load, so P generated by the PV plus P generated by the BSS is greater than the P DC load. So extra power have to be fed to the grid. So the voltage is fixed, that is 230 volt or the voltage of the DC bus bar. So extra current which is generated, it should be fed to the grid. So suppose this is the current level when the generation is low. So if the load is higher, if the load is reduced, this current will be moved to the higher level into the grid system, because it is generating higher, because no load is connected, means less load is connected in the DC. So this is the one behavior of the system. If the generation is more and the load is less, then the extra power is being fed to the grid, and their current magnitude will increase. And the second test case is such that if you have a similar power generated PV and the BSS, but the power generated by the PV plus battery energy storage system is less than the PDC load. In this situation, what will happen, that the grid current, the extra power is taken from the grid to maintain the DC link voltage. In this situation, your current will drop down in the grid side. Okay, so this is the current which is dropped down, and this is the actual current which of the DC grid. So this is the one situation. That two situation can occur, that when the generation is more, when the generation is low. So this whole setup is actually PHIL demonstrating this lecture itself, that you have a simulation environment in the RS-CAD. You have all the system, the DC sources and all into this simulation RS-CAD system. Then you can use this GT-AO card and the GT-AI card. How you can use this? Suppose you have a DC microgrid setup inside of that, and you wanted to use this power amplifier. In between, you need this because power amplifier accept the digital output. So analog input. So this RS-CAD will generate this digital signal, and this GTAO pin will generate, taking the digital signal and generate the analog signal. Then it is fed to the power amplifier based upon the voltage and the current level. Then this is the DFIG based control setup inside of that. Then it is fitted into the system. Then voltage and current center will give this voltage and current reference, and this signal is the analog. Then again it have to be converted into digital domain to fed to this RSCAD to do a PHIL setup, PHIL loop. Why it is told this power HIL? Because it is involving a power change level. Power change level means low level power to the high generating power, which is the actual system, is being taken care of by this power amplifier. That's why it is known as the PHIL. If it is simply HIL, there will be no power amplifier stage. So always remember that this is two cards which are very important for converting this analog signal, digital signal to analog signal and analog to digital signal. This card is being used. GTAO card and the GTAA card. Actually, this is the analog to digital converter. And if you see, this is the actual DFIG hardware setup, which I have told that this is the taking this power after power amplifier. The signals are feeding into the DFIG test bed. So this is the unit one, because you need to simulate this wind power. No? This wind generation is being simulated using the DC motor, which take the power from the AC system itself and convert into the DC. And this DC using chopper and also this DC converter, then it is fed to the DC motor of the 2.5 kilowatt. And after that you have a DFIG setup which have a two converter, that rotor side converter and the grid side converter, and it's have a separate control logics for this, that this is RSC control and the GSC control. And if you see that for converting to this grid site level, you first convert this GTAO card. GTAO is the taking the digital input and converting to the digital output, analog output. Then some calculation, this power amplifier stage is there, then it is converted again to this analog to digital converter. Okay, using this analog to digital converter using GTI card, and then fitted into this actual system. This whole system can be emulated into the one environment, that is the this D5G emulator is there. Then this GTIO and the GTI pin are being used, utilized for this conversion of the digital to analog and based upon this power amplifier. And this is the actual setup that GTAO pin, if you see that this is there. RSC, GSC, chopper and the FPGA based control, and DSO, RSCAD, induction machine, the DC motor. This is a whole setup for generating this wind simulator is there. So generally using this induction motor and the DC motor, coupled DC motor and induction machine, and the GTI and the GTO cards. This is the two racks are there. And one more thing is that this is the GTI card have is actually similar to this behavior, that it have a multiple pins are there. You have to specify that which pin you are going to use for the ADC conversion, and after output you should fit to these filters. Same with the GTIA card, it also have a real-time simulation. You have to specify that which pin you want to use. This is actually the one laboratory setup which will there, which take care of this system. But only thing is that you have to fit in that which pin you want to utilize. Coming to this next topic, that is the peak energy management using storages. Suppose this is the power curve of a PV generation, and this is the load curve is there. So if you see that this is the morning peak is there, morning peak, and this is the evening peak is there, and load is less into this afternoon session. So afternoon, this is the this power lean. It's said as the power lean. And in this situation, if you have a surplus power, you should feed to the means for charging the batteries or feeding to this loads itself. So for leveling this power generation, okay. So this reverse power curve also flow into the system, that taking the power for the batteries and that giving power from the batteries itself. So I have one question related to VSS. So again one VSS. So you have to tell me that which statement are true related to this. You have a 5 statements are there, and you have to tell me that which statements are true and which is false. Anybody wanted to give the answer? So that one first is false. If we use converter, we can change to DC store energy in the batteries.
Hello. Sir, for every statement, I'm
Yes,
having
yes.
some doubts. Second one, I'm not sure what is short term and long term.
Okay.
Third one, I have idea like it will be
Okay.
RT round trip efficiency of the bus will be in the range of 85 to 90% we can achieve of the PCC. And
Okay.
fourth one is false. Fifth, low cost means
Okay.
that's the doubt whether it is low cost or not. Yeah. Yes.
Okay. Okay. I will explain that. Anybody else want to give the answer? Srilata or Devendra? Okay, let me explain the few things here. First statement is there that is saying that battery energy storage system can only store energy, electricity generated from the renewable source such as the solar or wind. Actually, that is false actually one sense because it can store from the any sources. Suppose the generation of the wind and the PV is not that much, so it can take the power from the grid itself to maintain the DC link voltage and the charge the battery. So first statement is false. It can take the bidirectional flow is possible in the power in the battery itself. It take from the grid also, and they take from this PV also. It can take from the wind also, and it can send the power from the to the grid also, and take the power from the grid also. So first statement is false. Coming to the second part, it is saying that the BSS can provide both short-term and the long-term energy storage solution, offering flexibility in the managing energy supply and demand. There are two terms are there here. One is the short term and other is the long term. Here short term means suppose you are grid need a sudden changes power in change in power is there in the grid and the frequency dip down to a lower level. In that situation, there is a need that it should provide a power in a less than in the range of the millisecond or the microsecond. So this is a kind of a short solution. Short solution means only to provide a transient solution, transient power during for a short duration, transient power chain for the support of the transient power chain. But the long term is solution is that when the grid is not there, suppose there is a grid connected system and the peak hour reduction you want, peak saving you need. In that situation also you can provide a use the battery energy system for this peak hours and the peak saving. So this is a long-term solution. Means you are utilizing for a hour means multiple hours. Okay, but the short term energy storage solution is for transient support to the grid. Transient support for a millisecond or the microsecond. Long term is for the hours. Okay, so this is true. Coming to this third part, that efficiency of the BSS refer to the percentage of the energy input that can be retrieved as an output with the typical efficiency ranging from this. So BSS is such that this is BSS is the battery energy storage system. It takes the power for the charging and give the power during the discharge. Okay. So percentage of energy input that can be retrieved as a output is the efficiency. That is true, no? Why? Because if you are storing the power, suppose you have this battery capacity is 20 kilowatt hour and you stored at 19 kilowatt hour and you sending the power of 18 kilowatt hour. So efficiency will be such that you are sending 18 but charging to up to 19. So this multiplied by 100 is the efficiency. And typically it ranges from 70 to 90%, not 100% because the converter losses are there into the system. So third statement actually is true. Fourth statement saying that PSS can only be used for storing excess energy power. They cannot discharge stored energy during peak demand period to support the grid. That is false, because it's needed for peak saving for the utilizing and reducing the peak consumption during that duration. Suppose this is the load curve, and this is a morning peak and this is the evening peak. So in the morning peak and the evening peak, you can use the battery energy systems for the solution for reducing this peak, and you can utilize this power for charging during the off peak hours, and you can level this curve. Okay. And the fifth, it is saying that lithium-ion batteries are most commonly used technology in the battery energy storage system due to their high energy density and relatively low cost. Here, the cost term has been actually misunderstood in this question. That suppose you have a lithium-ion and you have a high energy density. So, how much time you can utilize? Suppose you have a means a 20 kilowatt hour battery pack, and you can utilize it for 10 years. Okay. And same lithium ion, and you have a sodium ion cells are there, you same capacity, but you are utilizing for the 5 years. So in this situation, which means technology is more costlier, which battery technology is more costly? It's a sodium ion, obviously, because it's you have invested money, but you are getting utilized for the 5 years only, but you are sending here the some money, but the cost benefit analysis, if you do here the this for the lithium ion, it's actually high. So in that sense, it is actually having the lower cost, because you can use for the longer terms. It have a high energy density and a higher power density also, and the cost in that situation it is low. Always remember that the cost is actually, when you increase the energy density, the cost actually lowers down. Okay, so by increasing the energy density, the cost reduces. Okay, so in that sense, it is actually cheaper in terms of the energy density and the replacement wise.
Sir, like you are
You can
saying,
ask.
um, based on C rate, like 1C batteries are higher cost than 0.5C or 0.2C, like that. Higher energy density means 10 kilowatt by 20 kilowatt hour.
No, 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 no. Actually, you misunderstood that. Energy density is such that what amount of energy. Suppose the batteries have a ratings in the ampere hours, and the voltage is of a battery pack. So voltage of the battery pack multiplies by the current rating is the whole of the energy density of the system. So it is said that suppose you take the one cell with a certain ampere hour and a certain voltage level. So initially what was happening, that the energy density was low and the cost was higher. So as the technology got improved, the energy density got increased and the cost in the same fashion it got reduced. For the clarity purpose, you can take this see the lecture of Professor Jhunjhunwala sir of IIT Madras of this EV based technology, and where you can get this clarity that how this energy density, if the energy density got increased, the cost got
Okay, sir.
reduced. Okay. Okay. And also one thing that energy density don't compare with this C rate. C rate is a different concept, that suppose you have a 20 kilowatt hour battery and you want to utilize it at a one go. So you can implement for 1 hour, you want to take that, you have to give this 20 kilowatt in a 1 hour to charge this battery. Okay, so this is a kind of C rate, that 1 hour, 2 hour, 3 hour, what amount of power. Suppose you want to charge in the 5 hour. Okay, so the same amount, your density, your 4 kilowatt power you have to give for charging this. So based upon that, that is a different concept of the charging and discharging. It depend upon the how much power you are feeding into the system. Okay. So there are four revision topics I have put it here. That is the control aspects of the BMS. Because you have a battery pack, you must have the BMS also. And in BMS, I have already told in the few previous lecture that you have multiple cells are connected in series and parallel based upon the current and the voltage rating. And inside of that, central system is the BMS, which senses this voltages and the current, and this contactor control also there. And then it is connected to this sensors, that is a voltage ampere ammeter and the temperature sensor. Then it is fed to the model based algorithm for the estimation and the prediction of the SOC, cell capacity, internal resistance, and then it is calculated the energy and the power. So there are two things are there. One, it is measured, and the second is the estimated, and third is the predicted. So measured values are voltage, current, and temperature, and the predicted value, estimated value are SOC, cell capacity, and internal resistance. And what is the predicted value? Energy and the power. Okay. And this is the one ECM cell which I have taken, and this is the basic electrochemical cell model. If you see here, so this is the R0 is the internal resistance, and R1 and C1, this is the diffusion effects, and hysteresis effect is also there, because the when the battery charges and when battery discharges, it don't follow the same path. So in between, that difference between their voltages level is actually represented using the hysteresis. And OCV is the open circuit voltage, which is a function of the SOC. Okay. Second topic is that what are the techniques for the SOC estimation? There are various techniques, and the most robust is the Kalman filter based. Kalman filter based technique is such that it have a certain component inside of this hardware and some other in the hardware software. So using sensors, you measure something, and using software, you predict something. Then compare both values, and after that you take the error and then optimize based upon this filter algorithm. So this is the topic. So actually I wanted to tell you that because the if you see in the image also, figure 2, this SOC yellow color is actually of the Kelvin filter base, and other is the with the Coulomb counting. So this is the, don't go into the flowchart and at all, only you have to remember that how it is being implemented, that in the software and the hardware. The second point I wanted to highlight is the contactor control. Contactor control is such that you directly don't put the batteries which are connected multiple cells, don't put the battery directly to the this DC load. So you need to apply certain changes into the system, that you should not connect this positive and negative contactor directly to this bus bar, okay, or the load. So what happened that you first close this negative contactor, then you uses this pre-charge circuit. Pre-charge circuit is of connected to this of a lower voltage rating, which have a resistor in between. So voltage will be reduced, so the higher current is avoided across this DC, because I is equal to C dVc by dt. No? So if you are connecting all the voltages V minus 0 at a few seconds, so the current will be very very high. So if you are doing in a stage wise, suppose V minus V some dash by some time, so this current got reduced. So this is the main crux, that you should not apply directly both the terminals at a one go. You first close the negative contactor, then close the pre-charge contactor, then positive contactor. And few other topics are like intelligent controller for the fault detection. There are multiple issues in the batteries also, that is overcharge, undercharge, short circuit fault, electrolyte diffusion, voltage based fault, and the short circuit fault. So I have given the some characteristic and advantages. You can go through that, and these are the methods which is being used for the detection and the clearance. And this slide will be shared, and you can go through that, and if you have any doubt, just text me it out. And these are the controllers, which is the passive cell balancing and the active cell balancing. And myriad methods are there in the passive cell balancing, such as the fixed resistor, switch resistor, and in the active cell balancing, that is the voltage measurement, without voltage measurement, PI based, wave trap based, and these are the multiple techniques are there. Okay. And these are the wave trap based active cell balancing. Wave trap means you have this switch. This is actually two level switching device is there, and you have a L here is there, and one trap is there, basically providing a resonance between this L and C filters. And if you have a voltage imbalance is there, but during the resonance it can send the power, because if the resonance is there, the battery will be get open circuited, the capacitor will be open circuited, that cell will be isolated. In that situation, that depending upon the resonance condition creation, you can switching off and on the devices, means battery at a particular level. So these traps are being used for the cell balancing. I have given the impedance also at by using the frequency change, you can make this Zi as a infinite, and at that particular situation that Zi got increased and this system got isolated. So the extra power which is there inside of the battery, it is being transferred to the other systems by using this method, this logic. Okay, this is the wave trap based method, and the last topic here is the isolation sensing. Isolation sensing is that if you have a chassis, this is related to the batteries and all, and EV basically. If you have these batteries are there, so you should not connect directly this to these chassis directly to this battery. So you need a certain resistor, that is the R1 and R2 and all. So by that you can connect this chassis. So these values are being calculated using some methods by creating a fault in the one right side and the fault in the left side. By that the R1 and R2 is being calculated. So if you are interested, you can go through this slide, but otherwise this is not necessary for this lectures and all. And the last topic I wanted to that this I have already explained, that peak saving, minimizing power losses, line loading and all. So last topic here is the India's journey. India's journey is the like that many smart cities is being actually coming into picture. There are a lot of research potential is there, and the various PhDs are which are working on that. Many professors are working on that. These are multiple millions of projects are going on, means $1 million. So means potential is very high, and you can think of it working in that domain. And here the I have put it this operation control, this research R&D areas, and the components which is being incorporated in the distribution system in this pilot project, that is a advanced metering infrastructure, power quality management, outage management system, peak load management, distributed generation. These all are the actually the components of this distributed system. And the main R&D areas, if you see that this operation control and production of this VAM system, supervisory SCADA system, TSOs, that is a transmission system operator, distribution system operator, how this seamlessly operate during the cyber attacks and all, forecasting of the renewables. And the second topic is the ICT and the cyber security, that is a HAN system, WAN system, the wide area network system. And this kind of infrastructure is also growing, the cloud computing, data storage, big data analytics. These are the also one of the topics. And the other topic is the devices based technology. Devices means you are making something. Suppose you are designing a controller, converters, you are doing a coordinated operation and all, optimally designing this flexible power electronic converter. These are the one of the topics. And the other is the devices technology based on the converters, that is the means the devices level, that's the gallium nitride, silicon carbide based devices manufacturing and all. And the other topic is the main R&D area is the distributed energy resources storage and deployment issue, that is the policy, regulations, cost benefit analysis, interfacing issues of the V2G, G2V and V2H, and meeting transient and all. These are the inertial issues are there. So these are the main R&D areas which is being actually coming through into this modern power system, modern smart grid infrastructure. Okay, so I think time is actually heading more than that. So actually I'm stopping this lecture. So the last session will be there after this. It will be a revision based session before your exam, where I will put it some of the like numericals and all, numericals and small theory based question. By that you can utilize that for before the exam. Okay. So thank you so much guys, and if you have any doubt you can ask me now, and otherwise I will stop the session. Okay, fine then. Thank you so much and have a good day.